In this video, we're going to talk about flat circular coils, which is exactly what it sounds like. And first of all, we figured out what is the magnetic field pattern created by it. And again, we use the right hand grip rule to help us. Now, if we use the thumb to point in the direction of the current and the four fingers to point in the direction, or rather the four fingers to deduce the direction of the magnetic fields that they produce, what you will notice, for example, over here, okay, if your thumb points upwards along the arrow, your fields will look something like that. Okay, coming out on this side and going in on this side. Okay, so maybe I can just do something like this. Okay, and if I look at this one over here, you'll find that pretty much the same thing happens. The field will look something like that. Again, going in on this side, coming out on this side. And I can do this a few more times, several other areas. But what you'll always notice is that the field generally goes in through the loop and goes out of the page when you're outside of the loop. And so there is a very interesting way for us now to deduce this very, very quickly. Okay, and so what we can do, we change the way we use the right hand grip rule. Now use the four fingers to point in the direction of the current. And so in this case, your four fingers would loop around in a clockwise direction. And you notice that your thumb will then point into the screen like so. So your four fingers will point this way and your thumb will push into the screen like so. And that would represent the direction of the magnetic field inside of the loop, and the direction of the magnetic field outside of the loop is always opposite to what it is inside the loop. And so the magnetic field will basically be coming out the screen everywhere else. And that is how we deduce the magnetic field pattern from a flat circular coil. So, as before, we also need to calculate some kind of quantitative magnitudes of the flux density created by flat circular coils. And the formula given is B equals to mu naught Ni over 2R. So mu naught again is 4 pi times 10 to the minus 7 in SI units. N is the number of turns in the coil, so I can loop many, many times over here, right? So N is simply the number of times you coil around. I, of course, is the magnitude of the current in the coil. And R is the radius of this circular coil. And what is very important is that the magnitude of this magnetic flux density specifically refers to the flux density right in the middle of the coil and nowhere else. For the A levels, you are only required to figure out the magnetic flux density in the center of the coil.